Hi, everybody. My name is Chérif Matta. I am a professor of chemistry and physics here at Mount Vincent University. And today I'm going to describe to you two short stories about some aspect of the research we do in my group here at Mount Vincent University. Thank you for coming to my talk, and let's begin. So the first story that I'm going to tell you quickly without any technical details is about the mitochondrial bioenergetics, while the second story is about the interstellar environment. In other words, the chemistry that happens in the space between the stars in our galaxy. Someone said once, theoreticians can poke their nose into the business of everybody else. So as you can see here from the title of my talk, part of it is biological and part of it is astrochemical. One concerns itself with what happens in the mitochondrion, which is a cellular organelle that is responsible to produce the molecule that constitute the fuel of living cells, ATP. And the other concerns itself with a century-old problem of astronomy. So the first problem here, the main stars of this problem, so to speak, is Islam Matar, Peyman Fahimi, and Jean-Nicolas Vigneault. And we've studied ATP synthase, which is a molecular machine in our cells that is supposed to catalyze, in other words, speed up the production of ATP. ATP stands for adenosine triphosphate. And this is the general fuel of all living cells, and this is what makes us alive and pushes all the reactions that are non-spontaneous under cellular condition to completion. In other words, it's a molecule that is vital for our life, and we can produce in the order of our body weight per day of this molecule. Philip Siekevitz has coined the phrase or the term that the mitochondrion is the powerhouse of the cell. And according to Peter Mitchell's chemiosmotic theory, everything we eat is essentially converted into a proton gradient. In other words, a proton imbalance across the inner mitochondrial membrane, this corrugated membrane here with Christie. And you can see here, because the protons are positively charged, the fact that you have a lot of proton in the gap here between the two membranes creates a positive end of this membrane, or positive side of the inner mitochondrial membrane, the one of the corrugated one here inside. And the face from the inside is negatively charged. And these protons end up going through ATP synthase and via a rotatory mechanism. This is how eventually adenosine diphosphate and an inorganic phosphate are bound together to form adenosine triphosphate, which we need into the cell. And this enzyme is known to accelerate this process. So far, all is known. The novelty of the work comes from this hypothesis. And in the hypothesis here, you can see two strikingly different pictures, one on the left and one on the right. This is constructive interference, and this is destructive interference. Destructive and constructive of what? As I said, the proton gradient creates an electric field across the inner mitochondrial membrane, shown here in dark. But the difference comes if the enzyme itself has, due to its very structure, an electric field that has nothing to do with the proton imbalance and everything to do with its own structure and the distribution of charged amino acids on its surface. And if that's true, this is just a hypothesis, like it was confirmed later by our calculation, but at the moment it's a hypothesis. If that enzyme has a component of its electric field parallel to the proton imbalance electric field, they will add up constructively, and the resultant will be large electric field. And on the other hand, if that enzyme's electric field has a component that is anti-parallel, so pointing opposite to the electric field due to the proton imbalance, it will weaken it, and hence the resultant will be shorter. In terms of energy, it means that we have a new term that was overlooked in the literature that could be just due to the very structure of ATP synthase, and that would also depend on, for example, if there are mutations or something, it would change that contribution to the electric field here of the enzyme itself, and hence the question, the hypothesis, is turned into a question of whether we should add a new term to the all famous equation in every textbook of biochemistry that captures the Gibbs free energy due to the proton imbalance across the inner mitochondrial membrane, according to the chemiosmotic theory of Mitchell, and whether we should add or subtract a term that is due to the structure of the enzyme itself. The first publication of this work appeared in ChemCom, and the editor were very kind to put it on the cover of the ChemCom, and it seems to have attracted some attention because it appeared in the Chemistry World News here, and this is the title of the paper. Here it is in bigger size, and these are the authors, the picture of the authors of the work. Jean-Nicolas Vigneault is the principal programmer here, and Peyman Fahimi contributed considerably into intellectually, and both of them were supervised by Professor Tang Nguyen Deng at Laval, Université Laval, and both Professor Nguyen Deng and myself supervised Peyman. So the latter part of the work, which is we are about to submit the manuscript, is almost finished, is led by Islam Matar, who has just defended his master's thesis at SMU, and now he's on his way to do his PhD, and also Dr. Peyman Fahimi. The impetus for the extension of the work has been the subsequent publication of the structure of the human ATP synthase, because we obtain the structure, the crystallographic structure, and then we calculate the electric field around the structure, and this is how we get an estimate of the term in the free energy for the chemiosmotic equation. This is the main result. You can see here 17 species that we studied, and you can see that the human enzyme, in fact, has a destructive potential difference due to the electric field of its ATP synthase. So our ATP synthase in our cell, in fact, reduces a little bit the efficiency of intermediary metabolism in our cells. And that might result to reconsider the way we calculate calories in food, to perhaps reduce it a little bit. So that should be a good news, because then you can eat a little bit more. So ATP synthase, we found, is not only a catalyst, but a full participant into the biochemical energy transduction, which is a role that was overlooked before. Our finding may require some revision of the way calories are estimated in food, might need some minor correction, perhaps. The second story has to do with the diffuse interstellar bands. And this is a century-old enigma, and it's really a North American collaboration between Canada, United States, and Mexico. Professor Daniel Magis at both SMU and the Mount as an adjunct professor at our Department of Chemistry and Physics. Alice Surette, who is now Dr. Alice Surette, she did this work with us while she was a PhD student. She came here on an ELAP scholarship. Eilish Sullivan, who did her honors thesis with both Professor Magis and Professor Tina Harriot from the mathematics department at Mount St. Vincent here. Cercis Morera Boado, who was the supervisor of Alice in her PhD. And Professor Lou Massa, who brought this problem to our attention in the first place. Diffuse interstellar bands were discovered by Mary Lee Hager way back then in 1922 at the Lick Observatory And she discovered absorption line that did not change position with the movement of double stars. If we look at the spectrum of a double star, that is two stars that are going around the center of gravity, their common center of gravity, as the star approach or recede with respect to the observer, there are shifts in the Doppler line, in the absorption lines here due to the surrounding atmosphere of the stars. And you can see that the dark line here are moving back and forth and oscillate as we observe these stars in their motion around the orbit, around their orbits. Yet, there are lines that are unaffected by the motion of the stars. Hence, these cannot be associated with the atmosphere of the star, but rather with the gases and dust clouds between us and the star. There are 550 or more of these lines, these absorption lines of unknown origin in the visible spectrum you can see here. Yet there are only two lines that are of probable attribution to a molecule, and there's only one molecule that has possible connection with these lines, and this is C60 plus. All the rest are of unknown origin. No one knows what molecules are causing these absorption bands, and this is the question we're trying to solve here, but it's a very tough question. The first part of this work, or the first publication we had here, was really driven by Professor Tina Harriott and Professor Daniel Magis, who co-supervised with me, MSVU honors degree student back then and now almost PhD graduate, Fraser Smith, in this paper that we published a few years ago, whereby we have discovered 4 new families of highly correlated bands. Every pair of lines in this family have constant ratios of intensity, no matter which stars you're pointing your telescope at. And that indicates that they are probably coming or due to a common absorbing molecular species. Here is another work that was done now, led by Emily Smith, who studied the optical reddening, which adds more credibility to the families that we found in the previous work. And it is no coincidence that Emily Smith and Fraser Smith have both the same family name. Well, they are brother and sister pair. Emily was an honors thesis student here at the Mount as well, working with Professor Tina Harriott and Professor Daniel Magis and myself. The later work here in this paper that was published just this year took this work to another level. We tried to get molecular, and even though we couldn't associate any particular line with a particular molecule in this work, there are several important discoveries that we made on the side, including we discovered 2 new families of highly correlated diffuse interstellar bands. Daniel Magis mainly, and Tina Harriott and the rest of us, found very strong evidence that strengthened the case for C60 plus, which is highly debated to this day. Correlation between the 2 DIBs that are supposed to be related to C60 plus has been strengthened considerably in this work by combining the data from multiple data bank and extending the range of the correlation. And we still have found very strong correlation between these lines, the 2 lines in question, which support the conclusion that the 2 lines that were presumed to be related to C60 plus are indeed very likely to be so. So we can confirm that C60 plus is a probable carrier for the 9577 angstrom and the 9632 angstrom line. In this paper, Daniel Magis and co-workers propose that these ions, C70 plus and C72 plus, can also be sources of DIBs that were not proposed previously in the literature. We proposed that there is a third line, 9365 angstrom, that could also be highly correlated with the two others of C60+, which is a new discovery of a new line that is related to this C60+, and also further reinforce the case for C60+. We're really very fortunate to work with Professor Magis, who is a very noted astronomer with nothing less than an asteroid named after him, as you can see here in the Royal Astronomical Society of Canada page here. Here is a table from a scientific paper, not ours, but another scientific paper, where you can see his name listed here in the table for the asteroid that he discovered a few years ago. So we discovered 6 new DIB families, each one of them possibly associated with a unique molecular carrier of DIBs. We have reinforced tremendously the C60+ case as a carrier of the 9,577 and 9,632 angstrom lines. We have discovered the third line, which is highly correlated with these two others, 9365 angstrom, which also strengthened the case for the C60+. Finally, we propose a C70+ and C72+ cations can also be considered as new candidates for DIB carriers. And finally, just a few days ago, our historical note on Mary Lee Hager's discovery just appeared in the Journal of the Royal Astronomical Society of Canada. Before I close, here is a few announcements. These are 2 of the books that we published recently that cover other aspects of the research we do in my group. One is about quantum crystallography. The other one is about these are books on electronic structure. One is about quantum crystallography, which injecting quantum mechanics into the crystallographic refinement technique. And this is a book about electron localization and delocalization matrices, which is a mathematical object that describes molecules in order to use in the design of materials, into the predicting of action of certain drugs, into the prediction of certain corrosion inhibitor activities, and so forth. Finally, I'd like to introduce you to a conversation with a scientist, which is our YouTube channel made here at the Mount, in which we try to bring cutting-edge research to the general public, and I encourage you to go visit the site by scanning this QR code. And at the end, I'd like to thank the sources of finance for supporting our work. And also, I'd like to thank the emerging leaders in the Americas program, ELAP, for allowing Alice Surette to visit us for 6 months. And also to thank very much Amy Bray and Max Mason. This talk would be incomplete if we don't give credit to President Joel Dickinson, Dr. Laurie Francis, the Vice President and Academic Provost, Dr. Carrie Dowson, the Dean of Arts and Science, Dr. Jacqueline Hagan, Associate Vice President Research, and their team, especially Cecilia Correa and Kathleen Magid, Manager in Financial Reporting. Thank you very much.